In section 4.7, we will look at a final application of derivatives called optimization. In optimization problems, our goal is to find the optimal or best way of doing something. For example, we may want to maximize area or volume or minimize time. We may want to maximize profit or revenue or minimize cost. Since we'll be looking for an absolute maximum or minimum value, let's do a quick review. How do we find the absolute maximum or minimum value of a function? We know two methods. The first is based on the extreme value theorem, which says if f is continuous on a closed interval from a to b, then f is guaranteed to attain an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the interval from a to b. Recall that the absolute maximum or minimum occurs at either a critical value, meaning where the first derivative is 0 or does not exist, or at an endpoint, x equals a or x equals b. So the first method for finding absolute extrema is to look at the critical values and the endpoints if our function is defined on a closed interval. The second method for finding absolute extrema is to use the second derivative test for absolute extrema. It says, let f be continuous on an interval I with only one critical value x equals c in the interval. If the first derivative f prime of c equals 0 and the second derivative f double prime of c is positive, then f of c is an absolute minimum. If the first derivative equals 0 and the second derivative f double prime of c is negative, then f of c is an absolute maximum. Recall that the key here is to think in terms of concavity. If the second derivative is positive, then the graph is concave up, and so it makes sense to have a minimum. Whereas if the second derivative is negative, then the function is concave down, and so it makes sense to have a maximum. Notice that the second derivative test applies to any interval. It doesn't have to be closed like in the extreme value theorem, but that we are restricted to only having one critical value in the interval. Here is our strategy for attacking optimization problems. First, draw a picture of helpful and introduce variables. Look for relationships between the variables and construct a model of the form maximize or minimize some function f on some interval I. Find the critical values of f, meaning find where the first derivative is equal to 0 or does not exist. Find the absolute maximum or minimum values of f on the interval I and the values of x where this occurs using one of the following methods. If I is a closed interval, evaluate f at each critical value and at the endpoints of the interval. Or, if f has only one critical value in our interval, use the second derivative test. Finally, use your solution to answer all questions asked in the problem. Note that the difficulty lies in the first step, determining the function to maximize or minimize, and determining an appropriate interval. After this first step, the problems are extremely routine. Take the derivative and set it equal to 0 to find the critical values. Prove the critical value is an absolute maximum or minimum, and answer the questions. Great, we're ready for an example. Your newly retired neighbor has decided to take up gardening. She wants to enclose a rectangular area with a fence. She has 40 feet of fencing material. A building is on one side of the garden and so won't need any fencing. Determine the dimensions of the garden that will enclose the largest area. What is the largest area? Let's read the problem again and see if we can draw a picture of the situation. We also want to determine whether we are maximizing or minimizing something and what it is that we're trying to maximize or minimize. Your newly retired neighbor has decided to take up gardening. She wants to enclose a rectangular area with a fence. She has 40 feet of fencing material. A building is on one side of the garden and so won't need any fencing. Determine the dimensions of the garden that will enclose the largest area. what is the largest area? Our picture is of a rectangular area with a building on one side and fencing on the other 3 sides. We don't yet know the dimensions, so let's say we have sides of length x and y. Our goal in this problem is to maximize the area of the garden. Based on our picture, our formula for the area A is x times y. Since we're looking to maximize a function, we'll want to take a derivative. But we can't currently take the derivative of a because it has too many variables, x and y. We must eliminate a variable before we can take the derivative. Looking at our problem, we were given another piece of information. Our neighbor has 40 feet of fencing. So we want to maximize the area of the garden subject to having 40 feet of fencing available. What is the equation of how much fencing we need? We need to build 2 sides of length x and 1 side of length y. So 40 equals 2x plus y. We can solve for y and see that y equals 40 minus 2x. Let's plug this in for y in our area equation. So we want to maximize a equals x times 40 minus 2x, or 40x minus 2x squared. Now that we have the function we hope to maximize, we need to consider an appropriate interval or domain on which our function makes sense. Since x and y both represent lengths of the sides of our garden, we want x and y to both be greater than or equal to 0. Hopefully this makes sense. We can't have a side length be negative. Since y equals 40 minus 2x, then y greater than or equal to 0 means 40 minus 2x is greater than or equal to 0. And we can solve for x by adding 2x to the other side and dividing by 2. So x must be greater than or equal to 0 and less than or equal to 20. Hence, our interval or domain for our equation is 0 to 20. The goal of our problem then is to maximize the function a equals 40x minus 2x squared for values of x between 0 and 20. Whew, this was the hard part. The rest is straightforward. To find our maximum, we first find the critical values. So we take the derivative. A prime equals 40 minus 4x and set this equal to 0. Solving, we see that x equals 10. Now we must check to find our absolute maximum. Since we are on a closed interval, we can evaluate our original function at our critical value of 10 and at the endpoints of our interval to see which value is the largest. So we plug in our critical value x equals 10 and our endpoints x equals 0 and x equals 20. Note that we are evaluating the original function here. The largest area is 200, which occurs when x equals 10. We now only need to answer the questions posed in the problem. We were asked to find the dimensions of the garden that will enclose the largest area and the largest area. We already found that the largest area is 200 square feet. To find the dimensions of the garden of largest area, we note that we found the maximum occurs when x equals 10. We know that y equals 40 minus 2x, and so when x equals 10, we have y equals 40 minus 2 times 10, or 20. Hence, the dimensions of the garden will be 10 feet by 20 feet. And we're all done. Let's review the process once more. Write the given problem as a function to maximize or minimize on an interval. Take the derivative and set it equal to 0 to find the critical values. Determine what the absolute maximum is using the extreme value theorem, as we did in this example, or the second derivative test, as we'll do in class. Answer the questions. Let's do one final example. Some airlines have restrictions on the size of items of luggage that passengers are allowed to take with them. Suppose one has a rule that the sum of the length, width, and height of any piece of luggage must be less than or equal to 150 centimeters. A passenger wants to take a box of maximum allowable volume. If the length and width are to be equal, what should the dimensions be? Our picture here is simply a box, and our goal is to maximize the volume of the box. We know in general the volume of a box is length times width times height. And we're also told that the length and width are to be equal, so V equals W squared times H. We can't currently take the derivative of V because it has too many variables. But we were given another piece of information which will allow us to eliminate a variable. The sum of the length, width, and height must be less than or equal to 150. So we want to maximize the volume of the box, subject to 150 equals length plus width plus height. Or, since length and width are equal, 150 equals 2W plus H. We can solve for H and see that H is 150 minus 2W. Let's plug this in for H in our volume equation. So V is W squared times 150 minus 2W, or 150W squared minus 2W cubed. Now that we have the function we hope to maximize, we need to consider an appropriate interval or domain on which our function makes sense. Since W and H both represent lengths of the sides of our box, we'll want W and H to both be greater than or equal to 0. Since H equals 150 minus 2W, then 150 minus 2W must be greater than or equal to 0, and we can solve for W. So W must be greater than or equal to 0 and less than or equal to 75. Hence our interval or domain for our equation is 0 to 75. The goal of our problem then is to maximize the function V equals 150W squared minus 2W cubed on the interval between 0 and 75. All right, remember this was the hard part. The rest is straightforward. To find our maximum, we find the critical values. So we take the derivative. V prime equals 300W minus 6W squared, and set this equal to 0. Solving, we see that W equals 0 or 50. We must now check to find our absolute maximum. Since we are on a closed interval, we can evaluate our original function at our critical values and at the endpoints of our interval to see which value is the largest. So we plug in our critical values and our endpoints into the original function. The largest volume is 125,000, which occurs when W equals 50. We now only need to answer the questions posed in the problem. We found that we have a maximum volume of a box is 125,000 centimeters cubed. We were asked to find the dimensions of this box. To find the dimensions of the box, we note that we found the maximum occurs when the width equals 50 centimeters. Since the length and width are equal, then the length is also 50 centimeters. And we know that the height is 150 minus 2W. So when W equals 50, H is 50 as well. Hence, the dimensions of the box will be 50 centimeters by 50 centimeters by 50 centimeters. And we're all done. That's all for our introduction to optimization. We'll have a lot more examples to work through in class together, and I look forward to seeing you there.